watch this later?
I'm going to turn off my video because it's
That's
small.
fine.
So.
Yeah. All right, so if you're looking at the very first one, it says the force acting between 2 point charges is F when the separation of the charges is X. And then it says, what is the force between the charges when the separation is increased? So this one, this is like an algebra problem, really. So let me show you kind of how I thought about doing this one. So oh, that's way too small. Hang on one second. Okay, so you have two charges, and usually they just name the charges Q1 and Q2. And what they tell us is that these two charges are separated by a distance of X. And they tell us that the force acting between the two charges is F. So what that really means is, so they tell us the force between the two charges is F. And what we need to do is use Coulomb's law to basically say, okay, F equals, that electrostatic constant K times charge Q1 times charge Q2 divided by the distance between them squared, which in this case is just X. So they tell us this, they tell us call the force between them F, and they kind of want you to make the kind of like the leap to be like, okay, well, the force is really given also by Coulomb's law. And so let's call this F, this force, we'll call it Fx to mean the force between the two charges when the distance between them is just X. And so what we want to now find is what is F of, let's call it 3X, when the charges are separated by a distance 3 times bigger. And to do that, what we'll do is we'll start using Coulomb's law again. So we know that it's going to be that electrostatic constant times charge Q1 times charge Q2. And now the difference is we're going to divide this by 3x, and we're going to square the whole thing. And so just to kind of do the algebra out now, the top remains the same. It's going to be Q1 times Q2 divided by 9x squared. And the goal for this problem was to see that if you just kind of carry the algebra out, so let me just kind of continue this out. You get K, hang on a second. You get K Q1, Q2 divided by X squared. And on the outside, if you want to just do some algebraic manipulation, you get 1, hang on a second. You get that 1/9, which is this term right here. So all I'm really doing is factoring that term out. And this term that's left, that K times Q1 times Q2 divided by X squared, well, that's just really equal to what we had to start with, that Fx. So this thing right here is just that term right here, which I've replaced over here. So for that very first one, the answer for that was going to be letter C. So this one was letter C. So number 1 is C. And so this one, I'll try to find other examples of problems like this, but they're actually pretty common. I think on that packet that I gave you, the one that I call, I think it was, there's a packet of questions called test 1. There was a couple of problems that were similar to this on that packet. So I'll try to figure out which ones those were, and I'll kind of send you a message to give you a heads up. Does this problem make sense though? Now that I kind of show it to you out like this? Yeah, like the hard thing about what you're doing right now with, like, you know, you're doing like a distance learning course basically, where you have a limited amount of time to see a lot of problems done out. And so that's going to make it hard. So don't feel bad about this test. We'll figure out a way. Like, I'm thinking about just giving like a makeup, like kind of assessment for it, like a thing to maybe replace this grade for everyone. Hang on one second. Let me show you how to do problem number 2. You were on the right track with number 2. So this is that one where they give you, they say you have like a charge here, and it's let's call this just like Q1, and that was -6 millicoulombs, not microcoulombs. A lot of people, when I was grading their stuff, they called it microcoulombs, and it was only milli. 0.4 meters, and then you have like an electron over here. And let's see if I have it on right. Do you have this? Let me just find it on my computer. Yeah.
Yeah, I do.
Okay. So in the future, like especially with assessments, use this. Like if you can print it out, it'll make it a lot easier for you. And I saw that you saw some of the values on here, but I just want to make sure that you can just find them a lot easier. So like on this sheet, they give you like the elementary charge. The elementary charge is the charge of an electron, basically. And then they also give you what's called the electron rest mass, and they give it as 9.11 times 10 to the negative 31 kilograms. Don't worry about this word rest. When we do relativity, you'll see that as an object approaches the speed of light, its mass actually increases. So like they consider this an electron at rest, quote unquote. Electrons are never at rest, but this just kind of helps us understand like some basic math terms, or excuse me, mass terms. Now for the first one, they said, show that the electric field strength due to the point charge at the position of the electron is 3.4 times 10 to the 18th Newton Coulomb. So what they're saying is they give you this. They say that the electric field, okay, which remember, it's going to be the force to charge ratio. So sometimes we write it like this. And what they're telling you is that it's going to equal 3.4 times 10 to the 8th newtons per coulomb. And so this is similar to problem number 1. They tell you like, okay, this thing equals this number. Show me how you get to that number. And so there's a couple of ways that you could do this. There might have been like, I forget, do you have this textbook? Do you have the textbook at home?
Yeah, I do.
Okay. What I'll do is I'll try to figure out like what are the relevant pages to read for this.
Okay.
Now, the way I go about a problem like this is, so a couple of things about this, just some background information. So the way that we think about the electric field, and I'm going to kind of, let me draw this as a separate picture. So we have this charge, and this is the negative 6 millicoulomb charge. And what they're saying is, or what they're trying to get you to think about this as, is this charge is going to set up an electric field around it, so that, and we draw the electric field with these like what we call electric field lines. it just kind of represents the strength of the electric force around this charged object. So like, as you get farther away from this charge, the electric force gets smaller and smaller. And we represent that with like force vectors that just get smaller as you get farther away. And what this charge does is it creates this electric field, kind of like a gravitational field around itself. And all other charges that show up or go through this electric field are going to respond to it. So one way to think about this is ignore that they're telling you that an electric they're trying to tell you ignore that there's an electron that shows up. Just find what the electric field strength is without the electron being there. And the way to do that, I think the easiest way is if we start with this equation that the electric field is going to be the force to charge ratio. Okay. So in this case, this term right here, the force is given by that Coulomb's law, which is K. In this case, if we want to think of it like this, it would be that charge, let's call it Q1. I think that's what I'm calling it. It's like that -6 millicoulombs times the charge of the electron divided by the distance between them squared, which they tell us. And then if we want to ignore that the electron is there for right now, this charge right here is going to be the charge of the electron. And what that lets us do is it lets us cancel this charge, the charge of the electron, with the charge of the electron here. And it gives us a way to think about what will the force between two or more charged objects will be if another charge shows up. So this equation basically works out to be just this, the electrostatic constant times that -6 millicoulomb charge times the distance between them squared. And in this case, I think what we can do, this is where we can actually plug numbers in. So if we just use K as 8.99 times 10 to the 9th, and that would be a Newton per Coulomb. Newton coulombs. And we're going to multiply that by this charge Q1, which was what, -6 times 10 to the -3 coulombs. And then we're going to divide that by 0.4, square the whole thing. And when you do that out, sorry, this is meter squared down here. Sorry, this is also should be a Newton meter squared per Coulomb squared. And this will be a meter squared down here. When you do this out, like when you plug that into your calculator, you should get this number, okay? So if you want to just check that later, I think that number does actually work out to be the same number there. And then so this was 2A, and then for 2B, I forget what you got for 2B, but for 2B, what you're actually going to do is apply Newton's second law. So 2B, so you're just going to apply Newton's second law. Bless you.
Sorry.
Yeah, no worries. So for this one, sorry, let me read what this was asking you to do. So this one says, calculate the magnitude of the initial acceleration of the electron. So let me just go back up here really quick, or actually, let me just draw it again right here. So you have this like -6 millicoulomb charge here, and you now have this electron over here. And then they say, okay, so basically what happens is, this is like what we call a textbook problem. This doesn't happen in real life, but like somehow this electron is brought into an area, and then now it feels the electric force between this charged object and this charged object. and it's going to accelerate. So there's going to be a force between, well, let me ask you this. So this is negatively charged, right? And the electron is negatively charged. So what kind of force, like, are they going to repel each other or attract each other?
Repulsion.
Very good. So the electron's going to want to go off in this direction. The electron, or this charge here, will want to go off in this direction. So what we're looking for is we're looking for the force of, we're going to call this one Q1. Q1 acting on this electron. And this is, so to do this problem, all we have to do is say, well, F equals mass times acceleration, because there's only one force acting on the electron. So to figure out the acceleration, it's just going to be whatever the Coulomb force is acting on the electron divided by the mass of the electron. And so for this one, I forget exactly what you did, but what oh, hold on a second, my tablet just crashed. Hang on a second. Hold on one second, I might have to restart my tablet.
That's no problem.
See if that works. Yeah, like, okay, sorry, this, I don't know what it is, but this keeps crashing my, I have a quick question. Do you know how to like force like something to stop on a Mac? Like, do you know how like on a PC you can hit Control Alt Delete and it kind of like stops something from crashing?
Adobe or the device?
Well, it's like, it's my tablet that, oh, it's the tablet that just,
like Finder and devices.
so, okay, hold on one second. Let me try to do a quick. I want to try to do, I'm going to stop recording for a second.